This is going to be a lesson on solving simple trigonometric equations. Now, if you're watching this video, I'd imagine you already know how to solve basic algebraic equations, but you've never really tried doing it when there are trig functions in the equations. So our goal for this lesson is going to be to introduce some of those equation types and actually solve them. Now, I hope that this isn't too much of a surprise to you by now. In order to do this, we're going to need to refer pretty heavily to the unit circle. Now, the first equation we're going to try to solve is x equals the cosine of theta. Now, when you're actually trying to solve an equation like this, you're being given the x values, and you're trying to solve for the values of theta that give you this x value. Now, I've just drawn in two of the possible answers over here, but we actually run into a really big problem when we try solving this equation. Because all of the trigonometric functions are periodic, you could start with this point and then go all the way around the circle one time, two times, or really as many times as you like, and you'd keep coming back to the exact same point. So if we're going to want to solve any equations that contain trigonometric functions, we're going to have to restrict the input angles that we can put in. So just to give you an example, we might say that we want these input angles to be any number between 0 and 2 pi radians. Now this is just one possible equation, but we can also go ahead and solve y equals the sine of theta as well. Now for this equation, we're actually choosing a y coordinate and finding the values of theta that hit that particular y coordinate. Now just like the last case, you can see that there's going to be more than one angle that gets you this same y coordinate. And then the final equation we're going to want to solve is going to be the tan of theta, which is also going to follow a similar process. Now remember that the tan of theta is just the gradient of a ray from the origin. We can visualize the gradient by casting out a ray from the origin and seeing where it intersects this line at x equals 1. Now anytime you're faced with an equation that involves trigonometric functions, you're going to want to follow the following process in order to solve it. Firstly, you're going to want to make sure that it's all written in terms of only one trigonometric function. Next, you want to make sure that you can write the whole equation so that it's equal to 0. And then you're going to want to use the inverse trigonometric functions to solve for at least one of the angles. After this, you're going to use symmetry to find the answers in the whole domain that you require the answer to. Now, so far, I've given you some general steps, but I've been a little bit vague. In order to actually make this a bit more concrete, I'm going to go ahead and give you some actual examples, and we'll try them together. So here we'd like to find all the values of theta that make this equation equal 0 over the range of 0 to 2 pi. Now, firstly, we want everything in terms of one trigonometric function, and here we actually have two different trigonometric functions. So the first thing we're going to do is we're going to divide both sides by one of them. I'll just go ahead and divide both sides by the cosine of 3 theta. So we can go ahead and break up this fraction on the left. And we also know that 0 divided by anything is always 0. We also know that anything divided by itself is also 1, so I can change that too. Now we just have to realize that the sine of anything divided by the cosine of anything is just the tan of that thing. Now that everything's written in terms of one trigonometric function, we should go ahead and try to solve for one of the angles. To do this, I'm going to move this 1 to the other side and use the inverse of tan. Now that we have this equation, we can go ahead and take the arctan of both sides. Now we know that in the general case, we can't just cross both of these off, but because we only need the first angle, we can actually go ahead and cross off tan and arctan straight away. Now this is the point where I actually go ahead and draw a picture to help me find the rest of the answers. Now if you went ahead and actually typed this into a calculator, you'd notice that it's just equal to 45 degrees or pi 4 radians. Of course it's negative, but I only really care about its size for now. Now I'm going to go ahead and replace this arctan of -1 for all the possible angles that we could hit when we keep going around the circle. Now I'm going to just start at minus pi 4. Now the next angle would be pi minus pi 4, so that's just 3 pi 4. And then the next angle would be 2 pi minus pi 4, and that's just equal to 7 pi 4. And now I'll continue doing this for a while as well. So when we write this, we're saying that 3 theta could equal any one of these values. Now to actually solve for theta, we want to divide both sides by 3. So what we're going to do is we're going to divide all of these guys by 3, which makes all the denominators 12. Now, if you type any one of these answers into the original equation, you'll find that all of them satisfy it. However, we did say that we wanted answers between 0 to 2 pi and nothing else. Since this answer is negative, we know that it's definitely not in our domain. Now, 24 pi on 12 is the same thing as 2 pi, so this answer is too big and therefore it's also not in our domain. So in general, if you want to find all the answers, you keep increasing the value and decreasing the value until you find the first values outside of the domain that you've provided. And now I'll go ahead and show you another problem that's also very similar, but also different in some ways. Now this equation is very similar to the last equation, but this time our domain is actually different. And we also have a cos squared, and we're going to need to figure out how to deal with that as well. To write this all in terms of one trigonometric function, we're going to want to remember the Pythagorean identity. Since the cos of theta squared plus the sine of theta squared is equal to 1, we can go ahead and solve for the cos squared of theta by moving the sine squared theta to the other side. Now we can just go ahead and replace cosine squared theta in the original equation. Now we can go ahead and expand the 6 out to the 2 other terms as well. Next we can go ahead and add this 6 and this minus 4 to get positive 2. And just because I like the number in front of this 6 to be a positive number, I'm going to go ahead and replace all the minuses for pluses and all the pluses for minuses. And now again, we've completed our first step. We've written everything in terms of sine theta. Now to solve for one of the angles, it's actually going to be a little bit trickier, because this thing over here is actually a quadratic. Just in case you didn't see this, let me go ahead and make the substitution sine theta is equal to s. Now, 6 times sine theta squared is just the same thing as 6s squared. Minus sine theta, which is just minus s, and then you've got minus 2. So 6s squared minus s minus 2 is just the same thing as this equation over here. Now, assuming that you're comfortable with factorizing quadratics, we can go ahead and rewrite this in the following form. If you expand this bottom expression, you should just get back to the one above it. And now we just have to realize something. If we're multiplying this and this to get 0, then either this first term is 0 or this second term is 0. Either one could be 0 and you'd still get 0. And now we just have two equations to solve. The first thing I'm going to do is I'm going to make sine theta the subject of this equation on the left. And now I'll just go ahead and take the sine inverse of both sides as well. Now we can go ahead and draw on a unit circle to just help us find all of the values. Now if you look really carefully, I hope you just notice that this is one of our special triangles, and that this angle over here is just going to be pi on 6. If you didn't notice that, you can also get this answer from your calculator as well. It's going to be pretty hard to immediately see that it's pi on 6, so what we can do is we can divide the arcsine of minus 1 on 2 by pi. Now remember, your calculator may actually have the sine inverse written in a different way. Now since this is just equal to this, if you multiply this pi over to this side over here, you'll see that the answer is just pi on 6. And now if we look at our whole domain, we also notice that we have an angle over here that also satisfies our equation. To get to that angle, you just go backwards by pi, and then you come forward by pi on 6. So this is just negative 5 pi on 6. And now we can just go ahead and repeat these exact same steps for this equation over here. Again, we can also take the arcsine of both sides to solve for the first angle theta. Now, if we type this value into the calculator, we'll notice that this one is not nearly as nice as the one on the left. If we go ahead and draw on a unit circle, we can visualize the two answers we're about to get. Now, the other angle, which is this one over here, can be found by going to pi and then coming back by 0.73 as well. And this means that our other two answers are 0.73 and 2.41. For these answers I just used approximate signs because I had to approximate the answers. And with this we've actually completed our example. So now, just to review, in order to solve any equation involving trigonometric functions, you want to write everything in terms of only one trigonometric function, solve for one of the angles, and then use symmetry to find all of the other answers. And we have to be careful to make sure that all of our answers lie inside of our required domain. And with this, we've actually completed our discussion on the simple trigonometric equations.